Double check the recorder. Yep, it's all recording. Good. I need some kind of a script to automatically start the recorder when I sign in. Actually, it wouldn't be too hard to write one. It's just okay. So now it doesn't really matter because the internet access is not functioning anymore.
It's Waldo.
So let's check. Nope, server not found.
That's weird.
Okay, so let me check this. Maybe I just need to rerun the D2CV server thing, which usually means if something else is broken already. I need to run this again. Try again. Doop. Fantastic. But wait, there's one more way to teach this class. I can tether the laptop to my phone to go get onto the internet. So let's try that. Okay, but I need the cable first.
We have the technology.
But
maybe
do we
not
have the cable? Yes, do we have the right cable? Yes! No. Oh.
What are you looking for?
I'm looking for a micro USB cable. They used to have one when we had a cordless mouse. So,
Come here often.
do you guys see any cable coming out of the back of the computer that has a micro USB interface?
Cannot tell. It's a lot.
That's what used to attach to this thing.
You can sacrifice your mic, maybe.
No, the mic is not micro USB. Yep. Oh, you got one? Thank you. Thank you. Just remind me to retry it. I got one.
Yeah, there's no free slots back there.
Okay. So we'll tether the phone, so now I have 4 USB devices attached to the computer to teach the class. Okay, so most of you are not getting it. I was making a joke in the earlier class that how I needed 3 USB devices attached to teach my classes. Now I have 4. Okay, so I need to go to my tethering.
Plug in a
Or tether. There we go. Okay. And out of the 4 USB slots in the front of the computer, I have used up all 3 already. USB tethering, turn on. Okay. Let's check. Do I have an IP address? Yeah, looks that way. 42116. That looks like a IP address. And I go onto the internet. Yes. All right. Thanks to modern technology, T-Mobile, and the micro USB cable, now we have connectivity to the internet again. And yes, this is all getting recorded, so I can present it to the district and ask them, what happened to the network? Okay, so getting back to this class, so we'll go to refresh, it's all good. All right, so what I want to do is to go back to the homework assignment, just to present one last bit that you need to know in order to do your homework. So here is complex numbers. And the last bit is added here. So additional information you will need is this part here. Because I never really taught you guys how to use the mult instruction, the multiply instruction. So I'll go ahead and show you guys a few examples of how to use the multiply instruction, just so that you know how to perform the multiplication. Because the complex numbers, I believe, has multiplication for complex numbers. So you will need to use multiply at some point. Okay? All right. So let's go to a terminal, pick one, and I'll just make a folder in a temp folder to illustrate how to use the multiply instruction. Okay. Mult.s. global underscore start, underscore start right here. Okay. So the mult instruction, MULT, only has one single operand. Okay. You can only specify one thing, which can be any operand. If I remember correctly, it might not take immediate as an operand, but it will take anything else as an operand. So let's say we want to multiply a particular value in a register to another value in another register. So let's say one of the registers is ECX. Okay, so we move L dollar. I don't know. Let's say 150 into ECX. ECX. There you go. Okay. So, but the mult instruction is done. The mult instruction only has one single operand. But how do you compute a product when you can only specify one number? You cannot. Okay. So the other operand is actually implied. The instruction mult implies that one of the other operands is EAX. So EAX is the implied operand. So that means if you want to multiply two numbers, one of the numbers has to go into EAX. So I'm going to put, 200 into EAX. So this way, the mult instruction, which is a signed multiplication instruction, which is what you need for your homework assignment, is multiplying 150 with 200. So the next question is, where is it storing the result? Okay, because with add, subtract, you're storing the result in the second operand. There's no second operand here. It's always stored in EAX and EDX. Okay, because when you multiply a 32-bit number with a 32-bit number, you can end up with a 64-bit number. How do you store a 64-bit number in a 32-bit number? You cannot. But you can store a 64-bit number into two 32-bit numbers, or 32-bit registers. So after this, I'm going to use comment to indicate the result here. EAX stores the least significant 32-bit of the product, and then EDX stores the most significant 32-bit of the product. Now this part is always the case. It doesn't matter what the operand is with the mult instruction, the end result, the product, is always stored in EAX and EDX. Is that okay? Now, there are two real implications from this observation here. The first one is quite obvious. Okay, one of the numbers that you want to multiply has to be loaded into EAX prior to the mult instruction. That part is fairly obvious. You cannot miss that part. The second part, where most people miss, is even though we are only interested in the least significant 32-bit of the product, because after all, the I and the R members of a complex is only 32-bit wide, it will always change EDX. So keep in mind that EDX is always changed by the mult instruction. Is that okay? Does everybody understand that implication and why it is important? If you were using EDX for something else, after the mult instruction, it will be overwritten. That's the bottom line. Okay? Any questions? EAX, I'm not too worried, because most of the time we do want the least significant 32-bit of a product. And most of the time we don't need the most significant 32-bit of the product, and then we forget that EDX is always changed. So you got to be careful when you use the mult instruction, and just remember that EDX is always changed by that instruction. All right? Is that okay? Yep.
Like, for example, what if you had something in EDX before the multi?
It gets overwritten.
But you can still use it as the operand?
EDX and EAX are the implied operands of mult. EAX serves two purposes. Okay, so if I want to give you the more general presentation of what the mult instruction does, let me switch to my notepad here. Okay, so this is the more general way to describe mult. So let's say we have mult and then some kind of operand. Okay, so I'm just going to say operand in angle brackets to basically indicate it can be a register, can be a memory operand. It's kind of flexible, which is kind of cool. So the result of this one is EDX colon EAX is storing the result of EAX times whatever the operand is. Operand. That's the result. And the notation of EDX colon EAX simply means EDX is responsible to store the most significant part, and then EAX is responsible to store the least significant part. But that's basically what is happening. Every time you execute the mode instruction, that happens. Is that okay? Did that answer your question?
Well, my main question is for the operand and bracket, is it possible to use EDX for that?
Yes, you
operand?
can use EDX too. Yes. So EDX and EAX can both serve as the incoming operands as well as the part that stores the result. Okay. I did not understand the question originally. Okay, so that's good. Are we okay with this one? Okay, all right. Any other questions about this one? Yep.
I already worked on the multiply subroutine,
Uh-huh.
and it complained about mult not being a valid instruction. Complain.
Okay, are you using the 32-bit?
Yeah.
Okay, let's go ahead and check it out. Just need to open a terminal. Yep. Mhm.
How do you have multiple terminal tabs?
Oh, to open up multiple tabs in a terminal, but this may only work in Linux, so I cannot speak for CMD in Windows. It's Control-Shift-T, which is a shortcut key, but you can also go to File and then just say Open Tab. It's a pretty handy feature because you don't need to open up actual new windows, but it also makes navigation sometimes a little bit trickier. Okay, so let's go ahead and go into the virtual machine to check out. I can just write the whole thing again. Because the question is whether the mult instruction is just mult itself. I'll just do this part. gstat-o, mult.o, mult.s. You're right, there's no such instruction.
Glad we have someone that started on the homework.
I used MULL instead, and that seemed to work.
Yeah, without the T.
Yeah.
Yep, there you go. Thank you. So let me fix the description in the homework. It's MULL. The second L is for long. Yep, exactly. I'm just looking for all the occurrences of MULT. Replace all of those with MULL. Okay, that should be good. And save. There we go. Thank you. All right. So any other questions about this one? What about, do you guys know how to call a subroutine in assembly language to a subroutine written in C that returns a structure? Let's try that.
You have to push a whole bunch of stuff, yeah.
There's a very specific spot
Push
for
a-
it.
Yes, you're correct. We have to push a bunch of stuff, but the ordering
In the
of what
right
you need
order.
to push is important. Okay, so let's check out how to do that. So I will use an example to illustrate it. Let's see, what should I do here?
Can you actually draw the whole stack frame with the and with that hidden
Okay, sure.
return thing as well?
Yep. So that means that we have to switch to the document camera. All right. So the first thing I want to do is to basically present the original C code, and then we'll talk about how to do it. So let's say we have some kind of functions f, whether it returns anything or not is not even important, and then we have a struct, some kind of struct. I just call it type X here. It's not important what kind of structure we are dealing with, and we just call this my local variable X, and I say X equals to G and blah blah blah, whatever. Okay. So in function G, the return type of function G has to be specifically struct X, G, which does not take any parameters. At some point, it's going to return a structure. So struct X TMP for temporary, and that's what I'm returning. Okay. So is that readable or not? Doesn't look very readable to me. Can you guys read that text? Okay. All right. So we want to implement something like this, where this is the line that I want to implement. Okay. I want to be able to call a subroutine in assembly language, but I want to call a subroutine that may be written in C, that may be written in assembly, and the subroutine that I'm calling is returning a structure. And then I have to do something with the structure that is returned. In this case, I want to store that into my own local variable X. Is that okay? Because does it look like something? This is something that you need to know to get your homework assignment done. Definitely. Okay, very good. So let's go ahead and do this. Okay. So the first thing we want to do is to look at the perspective of the caller, which is this line of code, and go like, okay, I'm not too concerned about my own local variable X because, hey, until I get the result back from G, I don't have to do a single thing. So I can focus my attention and just say, okay, let's just call G first, okay? That's one way to look at it. The other way to look at this is to say, well, instead of allocating a chunk of space on the stack and then do a whole bunch of copying, what about I just pass the address of X to G as the hidden parameter? Maybe that's a better idea, okay? So this is a simple case where we can just, from the perspective of function f, to implement this line here, we have to first calculate the address of X, which is a local variable. To do that, and also I need to push it on the stack. And to do that, what we need to do is to push an address that is close to where we want it, and which register is already pointing to pretty close to where my local variables are. EBP, very good. That's the whole purpose of the frame pointer. Okay, so we push EBP first, and then we say, well, but that's not exactly what we want because EBP points to old EBP, and X being a local variable is somewhere below where EBP points to, right? So the address is a little bit below what I just pushed on the stack. That means I can just do the adjustment like this. Add long $x, assuming the label X is properly defined to be a bunch of bytes or a bunch of addresses below a 0, okay? So I can just add this number to whatever I have just pushed on the stack, like that one. So now I have just pushed the address of my local variable X on the stack. Is that okay? And after this, there's nothing else to do, just call G. G will do its thing. Remember this time G can be implemented in C. So, but whether it's implemented in C or assembly, as long as they follow the same convention, it will still get the job done. So when this is all done, this is the part that is a little bit. I need to adjust I think I did adjust my notes for this. Okay, so this is the part that is a little bit tricky. Is I don't need to deallocate these 4 bytes. These 4 bytes are actually deallocated by the callee itself. And there's no need to adjust for those 4 bytes. So let's check out this whole thing and see if it works in assembly. Okay, so we want to check out the whole thing. We'll go switch to a terminal and then we'll work on that code. And I'll just call it struct return. I'll work on the few files at the same time, so I will display these files side by side. One is main, which is written in C. The other one is written in assembly. Okay. Struct lowercase s. I want to show these side by side, so that becomes important. Okay, so let's work with the C code first. The C code is basically just saying struct x has several members. Let's just say it has int I. Oh, I did it at the wrong place again. Okay, before I go any further, this is the wrong place because this is not. No, it is the right. Okay, it is the right place. I was thinking I was still in the host environment, but this is actually in the guest environment already. So I'm using 32-bit in this case. Okay, and this is int y. And we need a semicolon at the end. You don't need that for class definitions, but you do need that for struct definitions in C. And then we just have main, struct x, which is the local variable x of main. And then we just have to say x equals to g. And this time we'll give it something to initialize. We will pass 2 parameters to g, and this is how we define g in C. Struct x g int. Let's call those I and j, and we have our own local variable in g. We call it temp. Temp dot I is parameter I, temp.j is parameter j, return temp. Okay. And return 0 down here. There we go. So now we have the C version of the code, which obviously doesn't do anything particularly useful. All it does is, G is kind of like a constructor. All it does is to initialize a structure and then return the structure that is already initialized. And then the whole thing is going to be copied into local variable x in main. So that's the entire C code. Do we have any questions about the code written in main.c? No questions? Okay. So if there are no questions, the first thing I want to do is to test the C code. So we'll do a gcc-o main.c. And we also want to remember to specify -g to include debug information. It complains about line 10, temp is undeclared. Okay, on line 10, oh, forgot to specify the x as the name of the structure. Do it one more time, it's all good. And then we'll just go ahead and we'll just put a breakpoint on line 20 because I just want to verify that this program does work. So we run the program, we are on line 20, we print x. X has a value of, has a member, the member I has a value of 2, member j has a value of 3, so the C code does what it's supposed to do. Is that okay? All right, so if this is good, then we are going to go back to this code, and this is the first time that we are going to implement main in assembly. We'll keep the rest, we'll keep G implemented in C, but we'll implement main in assembly. So that means we are going to, we will do this, comment out the entire main subroutine, and we'll implement it in assembly. So as usual, we have .global, whatever label we want to export is whatever we want to specify after .global, and then we have main, return. Now, main is no different from any other subroutine, so it has to basically follow the same rules and do exactly the same thing. So we're going to say push L EBP, pop L EBP, move L ESP to EBP, move L EBP to ESP, And we'll go ahead and define some of these names here. Okay. Now, since we don't have any we do have parameters, but I'm not interested in the parameters passed to main, so I don't need to define anything further than old EBP. But I have a local variable x, so I do need to define x to be old EBP minus whatever size it has to be. Okay. So I'm going to cheat here because instead of doing what your homework assignment is doing, which is relying on C program to crank out the include file that defines all the offsets and also the size of the structure, I'm just going to cheat and hard code it here. Okay, because I know that struct x has two 32-bit integers, so the size of that is just 8. Okay, so that's how I can just put an 8 here. Now, if you really don't like this, you can also say struct x underscore size of is 8, and then use that definition down here, which just makes it more symbolic so that when you read that line of code, you know why we are subtracting that amount. Okay? Okay, so with that definition, we can now say, okay, let's go here, and we want to add x to ESP. And what that will do is it just moves ESP down by 8 bytes in this case to reserve for the space for local variable x. Is that part okay? Okay, so now we just have to go ahead and implement the subroutine, which is x equals to g23. So we still have to push the parameters. Okay, we're going to push 3, which is the last parameter on the stack, push 2, which is the second parameter, which is the first parameter on the stack. But now we have a hidden first parameter. The hidden first parameter is the address where the return value will be stored. Now, there are several ways to do this, but the easiest way to do this is simply to say, oh, let's just put it into where x is supposed to be. Okay, so we'll go ahead and do it here. After this one, I'll show you another example where you can, I'll deal with that later. So now we have the code to push EBP on the stack and then adjust the address that is already pushed on the stack so it becomes the address of x. And in GDB, we'll double check and verify that calculation as well. Okay, so nothing will be left unchecked. Then we call the subroutine G. When everything is done, I claim that we only have to adjust the stack by 8 and not by 12. Because if you think about it, there are 3 push L instructions. So we used up 12 bytes on the stack for parameters. But the actual adjustment that I need to do is only 8. Because the called subroutine would actually get rid of the 4 bytes that is used by the pointer to the return value area. Okay? Which is something that you also have to account for when you write your own subroutines. Okay? All right, so when this is all done, we just have to return a 0, which is move L $0 into EAX. Because after all, main is just another subroutine. If it needs to return 0, we just put a 0 into EAX, and that's how we return a scalar value. Okay, are there any questions before we try to compile, link, and debug this code? Yep, go ahead.
So, like you're saying that the one that the code cleanup is the pushing of the EBP. Push L EBP and add long x $x to in parentheses ESP. Those 4 bytes is adjusted by the callee and not by the caller. And that's a weird deviation from what we usually do, but that's how the C compiler works, and those are the rules that we have to play by. Okay? So we're going to check everything along the way when we run this code in assembly. But conceptually, are we okay with this code? Yep, go ahead.
Okay, so when we're adding x to ESP, that's us allocating space for the local variable?
You mean on this line here?
Yeah.
Yes, we are allocating space for the local variable x. X is a negative number, so adding a negative number to ESP is reserving more space on the stack.
Okay.
Because you're moving the stack pointer lower.
Other question.
Mm-hmm.
what are we doing when we add the same X to the ESP before we call?
It
value
is
is-
for computing the address of X. We want to push the address of X on the stack. That's what we want to do. Okay, so let's give them line numbers. So this way it's easier to refer to the lines. Okay, so line 11 is quite obvious what it's doing. It's just pushing EBP on the stack. EBP is an address, right? It's the address of old EBP. Okay, but that's not what we want. We want the address of X. How far is the address of X away from the address of old EBP? The label X is representing that offset. So if we add that offset to whatever we just push on the stack, which is the address of old EBP, now we have the address of X.
Is there any way you could write that in one line, or is this the way you have to do it?
No, there's
Okay.
no. Okay, in one line you cannot compute the address and push it on the stack at the same time. In one line you can compute the address, but not to push it on the stack. Okay, are we okay with these concepts? So far, so good? Okay. All right, let's go ahead and check it out. Okay, so what we'll do is we are going to compile both the C code and the assembly code. .c, .s, and we want to supply a -g to mean that we want to debug the code when it's all done. Okay, so gdb main, and this time we want to put a breakpoint at main, which is no longer written in C, it is now written in assembly. So we run the code, and this is the main subroutine. It doesn't stop at the push out instruction for some reason. I think it does recognize the entry, the prologue of the C function, and it doesn't stop at that at those points. But it does stop, after that. So we now allocate the space. We push 3, we push 2, we push the address of X on the stack. Now we are going to call G. Now GDB is really smart. If you single step here, we get into the C code, which is great. Okay. Because now we can say, oh, are we really sure that we got the ordering of the parameters right? And I don't have to say a single word, because you can see on the screen that we are calling G, parameter I has a value of 2, parameter J has a value of 3, which is what the C code was doing originally. So we are good here, okay? So we say, okay, let's store I into temp, into the I member of temp, J the same way into the J member of temp, and we say, okay, what is temp? Temp is just 2, 3 in the structure, no big deal. Single step again, this is the end of the C code, single step back into assembly code, okay? You know what, I forgot to do one thing. I forgot to check the stack pointer before the call, then I can check whether we only have to adjust 8 bytes or not. Forgot to do that. But let's just finish this part here. Okay. So at this point, we are ready to return from main, which also means the local variable X in main is supposed to be initialized, because that's the whole thing that we want to check, right? So let's check that. Okay, can someone tell me how to test, how to see local variable X, which is now written in assembly, in main, to make sure that it does have 2 and 3 as the actual members in that thing, and not use the X command, because the X command is really primitive. It only shows you content of memory. It doesn't understand the concept of members. Okay, come on, you guys, show me your C prowess.
The I command?
The I command is not what I want to use either. I want to use a print, and I want to, the GDB, using what GDB already understands about the struct X, to print out the content of my local variable X. Okay, so let's see. Let's check how well you know your C casting capabilities. Okay, so I'll give you several clues. Okay, so we want a dereference at the end here. Okay, and the casting is a struct X.
pointer. Okay. All right. So we're casting something into struct X pointer, and then do a dereference at the outside, so that we'll be printing the actual members of the structure and not the address of the structure. So now the question is, how do we specify the address that we're supposed to get to? There's several ways to do it. Okay, we can hard code it. Yeah, go ahead. $EAX. Well, EAX doesn't have that E, right? Okay, so we do know that it's close to EBP, don't we? But EBP is pointing to old EBP and not quite the local variable X. So what do I need to do to EBP to get to the address of X?
Subtract 4.
Subtract.
8 or subtract 8.
Yeah, we can subtract 8. Okay, we can just hard code it. Okay, that works too, just like that. All right. So if we get 2, 3, we're good. Yep, we do. So that means, I followed all the conventions in C and C++ in order to call a subroutine that returns a structure and know how to deal with the return structure. Are we doing okay so far with this program? Okay, but one thing I did not do is whether the stack is balanced by just adding 8 after the call. So we'll do it again this time, but this time it's not going to be as long because I will set up certain breakpoints at the right places. So I set up a breakpoint on line 13 and set up another one at line 14. That's all I need. Okay, we'll run the program again, and this is the breakpoint in main, which is not important. Well, I suppose it is kind of important. Okay, step, step, step. Okay, this is the point where I want to print ESP or just IRESP to look at the current stack pointer. It ends with 704. So if my theory is correct, when we return from the call, it would have deallocated 4 bytes already, which also means the ESP, the stack pointer, should end with a 08, because 4 bytes would be deallocated by the callee, unlike the conventional way of doing things. Are we doing okay so far with that theory? Okay. So now we are ready to do the call. I already know the call itself is working, so instead of stepping into the call, stepping into the function, I'm using next to step over the function. It actually runs the function, but it won't stop inside the function. Okay, so now we are into the instruction right after the call. Look at ESP again. Oops, typo. And it is 708. So this is odd. Okay, so I do have to point this out because do we know how to do this part yet? How do we skip 4 bytes when we return and say, hey, we want to return, but at the same time, let's clean up those 4 bytes that is above the return address. Is that okay or not? Is this illustrating, some parts that you need to know for your homework assignment, which is to call a subroutine that returns a structure? What about a subroutine being called? Let's do that part in assembly, okay? All right, so let's get out of the debugger. We'll go back into our VI, and this time I am going to uncomment the main program. So this part will now be implemented in C, and then we'll comment out this part, which means this part will now be implemented in assembly. And on the other side, I'm going to use a different file, so I'll keep this file. I'll use another one called g.lowercase_s to implement the function s. .global g, and this time I do have parameters, so I'm going to use the old way of doing things, which is old EBP equals to 0. Return address is old EBP plus 4. We have the first parameter being the return value address, so we call it return value address is return address plus 4. Then we have I is return value address plus 4, and then J is I plus 4. Do we have any questions about
the allocation of those, the definition of those symbols. Yes or no? Is that good? Okay. The whole point here is we have an implied parameter. We have an implied first parameter, which is our return value address. It is a pointer pointing to where am I going to store the return value. Okay.
And if I implement this code exactly the same way as what it looks like in the C code, I have my local variable temp as well, which is going to be OEBP minus the size of a struct X, which we just know is 8, so I'm going to hard code it here. And now we can start with G, push EBP, move L, ESP to EBP, ending with move L, EBP to ESP, pop L, EBP, and return 4, okay? So unlike before, this is now a return 4 statement or return 4 instruction. Return 4 basically says, return, just like before. We also want to deallocate 4 bytes at the same time. So those 4 bytes that we are deallocating would be the 4 bytes above the return address itself. Okay, so now we can go back and implement the rest of this subroutine. The first thing we need to do is to allocate for my local variable temp. So we are adding TMP, the label, with a $sign to ESP, just to do the allocation. And then we can now do the, we can copy I to the I member, copy J to the J member. So that part is not too bad, okay? It's not super easy either, because I cannot have 2 memory operands, so I have to rely on EAX as the temporary thing to go between the 2 memory operands. Move L EAX to TMP plus I. Okay. I is the first member, so there's nothing to add, but I'm going to use 0 here to indicate there's nothing to add. Okay, let's just stop on this line here. Does everybody understand why TMP plus 0 and then in parentheses EBP is referring to member I of temp? Member I of temp is the first member, which means the address of I is the same thing as the address of temp. So if I want to store into I, it's really the same thing as storing into the first few bytes of temp. But if I just want to store something into temp in parentheses EBP is the way to do it. The plus 0 is just really to emphasize that we have a displacement of 0 from where the structure begins to the member I of the same structure. Okay. So in your code, do not hard code it like this. You have to use the labels that your C program is defining, so that way when I change how the structure is defined, it won't impact your code at all. So now we deal with J. So we copy the parameter itself into EAX, and then we copy EAX into temp plus 4 this time, because J is the second member, so it does have a displacement of 4 from the beginning of the structure. So these 4 lines will do the temp.I equals I, temp.J equals J. Now it is the return instruction. The return instruction turns into a mem copy, because what we're trying to do is we're copying the entire local variable temp to the place that return value address is pointing to. Okay, so we have to set up a mem copy. And obviously, I cannot remember, how mem copy works. In other words, the ordering of the parameters. I kind of have a general idea. I'm suspecting the first parameter is the destination pointer, the second parameter is the source pointer, and then the last parameter is the number of bytes to copy. But it doesn't hurt to confirm that. So I'm going to do a mem copy just to confirm that. Okay, so it does confirm my suspicion. Okay, destination is the first one, source is the second one, and then n, which is the number of bytes that I'm copying, is the last one. I also have to make sure I don't make the same mistake as last time, which is calling memset, even though I'm supposed to call memcopy. All right, so we have to push the last parameter first, which is easy because we just want to copy 8 bytes. And then we have to specify the source, which is the address of the temp local variable. Now, when you need to refer to the address of a local variable or parameter, this is the technique to do it, okay? You don't have to do it this way. There are several other ways to do it, but it's just the way that I'm used to. And now we have to push the address of the return value address. But the return value address is an address by itself. I'm not going to push the address of the address. I just need to make a copy of that address so that your mem copy knows where the destination is. So that one is relatively easy. I just need to push return value address EBP onto the stack. Then I can go ahead and call man copy. When it comes back, since I do intend to clean up the stack whenever I can, this time I'm going to add 12 to ESP to undo the 12 bytes that I push on the stack. And that should do it. Okay, that should specify how to return TMP. So this instruction here, or this statement in C, is being done by this chunk of code in assembly. Are we doing okay so far, or do we have any questions about the assembly language implementation of subroutine G? Is that okay or not? Now the main point, okay, if you have to remember one thing, is the last instruction. Okay, you have to remember that we have to offset the stack by 4 by specifying the 4 after the as a part of the return instruction. Yep.
So does this happen? This happen in like just every single structure function, or?
With every function that returns a structure, you have to do it like this. But with a 64-bit architecture, obviously you have to adjust the 4 to become 8 because every address is 8 bytes long. Are we still doing okay so far with this before we give it a test? Okay. There are no questions, then we are going to save the files and then gcc-g -o main.c and g.s. Unsupported instruction. Yep, go ahead.
Could you possibly upload this on Moodle so we can play with it?
Yeah, sure. But after I fix it.
Okay, thanks.
Okay, so the C function has a problem. Incompatible types when assigning. Oh, okay, I know why it's complaining. And then
return now,
no, the C function or the C program has a problem because G has no prototype. So what I need to do is to copy this part here so that G has a prototype, so the C compiler knows what to do with G. Now on this one here, that's not the right one, G.S, there we go. So the syntax is not return 4 like that. $4? Can't remember. Yep, $4, sorry. Because 4 is a direct operand, it specifies the address where I get something. $4 specifies the constant 4. So you need a $sign. Okay, so we do a GDB main. And this time the magic is in the subroutine G. But let's just look at everything from the perspective of the main program. So we'll list the program, put a breakpoint on line 23, run it, and we'll just do an N. Okay. But before we do that, we want to take a look at the stack pointer. Oops, IRESP. The stack pointer ends with E0, and then we'll do an N for next, because otherwise it will step into the subroutine, which is what I don't want to do at this point. So now we're at the return instruction, IRESP. It should remain balanced. So everything is good. Well, maybe not. It's easy to balance the stack. Did the returning actually happen? In other words, this is still in main, which means the local variable x in main should now have 2, 3 as the values of the member I and j. So let's check that. Yep, that also worked. So are we doing okay so far with the caller's perspective and the callee's perspective when you call a subroutine that returns a structure. So we're doing okay in both. Okay. What if you use the return value of a function that returns a structure immediately as a parameter of another function that passes a structure as a parameter? Right?
Sounds like a trip.
That was a really good question.
Okay, so let me just kind of give you the code. I think the verbal description may not be very clear, so let me just kind of give you the actual code. Okay, so the actual code is, let's define f as a subroutine. So f as a subroutine, well, do I want, yeah, f can do this. So struct x, f, it has a struct x as a parameter, which is passed by value, okay? And this is something that is also in your homework assignment. You know, all the structures are passed by value and they are returned by value as well. So this is something that is actually related to your homework assignment. Okay, so in this code here, what I'm doing is, let's just increment both members by 1, okay? So x.i plus plus, y.i plus plus, and return x here. There's no y, that's x.j, there we go. All right, so this is function f. It takes a structure as a parameter passed by value, and all it wants to do is to add 1 to each member of the parameter, and then return the parameter to whatever is calling function f. Is that okay? So now the C code of main can be a little bit more complicated. Well, in C, it is just a little bit more complicated because now x is the result of applying f on top of g of the 2, 3 as parameters. Is that okay? So now I cannot use the same trick as last time, because the same trick as last time won't work this time because it only applies to the outermost call, which is f. That trick won't work on g. I need to specify a place to store the result of g first. Is that making any sense?
When you say
Why not?
trick, you're saying for?
See?
When you're saying trick, you're referring to the for?
Return to the 4. No, not that. Okay, maybe this is not particularly tricky. Let's make this a little bit trickier. Let's have 2 of those. Oh, this is looking way too close to your homework assignment. I don't like it. I don't like it at all. Okay, we cannot do this. This is exactly the same code that you have to do for one of the subroutines. I cannot do this. Okay.
How do you code?
You can prove the code.
Name it a different
How about
letter.
applying like
I'm
an
still
end to
thinking
second
about the
parameter?
other.
How about just flipping them around?
Subtraction?
Hmm?
You can do subtraction.
Subtraction? Yeah. I think that's in your homework too. Okay, so the point is, I have 2 parameters, both passed by value as structures, and then this thing has to return a single thing. Okay. All right. So that means f needs 2 parameters, and the second parameter is going to be that. There we go. Okay, so this makes it a little bit harder because I cannot just use the space of x to do everything anymore. Whereas before, I can just keep saying, oh, okay, we can just reuse, x, because, x can store the value of g23, and then, x can be used to specify, the parameter for f as well.
But this time, I cannot do that anymore. So I really have to kind of think about, okay, how do we get this done? Okay.
So what we want to do is to, well, first of all, we want to take a look at the structure of what the call frame should look like from the perspective of G, okay? That's the first thing we want to see. And I'm going to rotate this again, because now I want to use a vertical, oh, I know what I will do. Do this, and I specify no rotation. Nope, I do one rotation, but not by 180. There we go. So this way I can. Oh, it doesn't quite superimpose the way I want it. No. Okay, maybe transform is gonna work. Yep. All right. So push it up as much as I can. There we go. All right. So what we want to do is to see things from the perspective of calling F. And then we'll work out how to deal with the individual G's, okay? All right, so by the time we are ready to call F, okay, what should the stack look like? Well, once again, we have the second parameter on the stack, then we have the first parameter on the stack, and then we have the pointer to the address that will store the result on the stack, and then we have the return address on the stack, okay? So that means from the call frame perspective, the first chunk of memory is going to store the value of G45, and then below that will be another structure that is storing the value of G23, and then below that is going to be a pointer. It's only 4 byte long to point to the address that will store the return value of F itself, which is only, that address is only 4 bytes long. So this is our return value address, which points to local variable x. And then below that is my return address. So this is how the stack should look like when I get into subroutine F. Is that okay? So somehow the caller is responsible to set up all this stuff on the stack. Is that making any sense? All right. So in terms of steps, how do we do this? This is the end result. First step. The first step has to do with G45. So how do we get G45 on the stack like that? First thing we need to do is to allocate a chunk of space here, which is the size of a struct X. We just allocate it on the stack. Yep.
I would like to take this moment to see if we're still recording, just in case.
Oh, that's a good point.
It's a lot of good information. That would be a shame to be lost.
Indeed. Yep, so it's still recording, and we'll double check. So I can.
We've got audio.
And we got everything going. So far so good. Okay, so switching back to my, oops, not that one, that one. So getting back to here. So the first thing we want to do is to allocate enough space for struct X, which is fairly easy to do, which is because we just have to move the stack pointer, ESP, to go a bit lower to that point. We know how to do that already, don't we? Subtracting something from ESP, right? Okay. Then we have to do something like this. Okay, this part is a little bit trickier. We want to allocate 4 additional bytes, which is going to be, oops, not yet. So we have 5 here, we have 4 here. So these two are the actual parameters to G. 5 being the second parameter is pushed first, and then 4 being the quote-unquote first parameter is pushed second. But since G returns a structure, it has an implied first parameter. We could call the parameter 0 if you want to, which is the return value address. So this is the return value address from G's perspective. Are we doing okay so far? Now the question is, where is it going to point to? In other words, my question is, where do you think these 4 bytes is pointing to? These 4 bytes is a 32-bit address. It points to somewhere in memory, but where is it pointing to?
Like it's something somewhere in G.
Something that's already in this picture, because I allocated a chunk of space for struct X for one reason. This needs to point here. Is that okay? And then the call itself is going to set up the return address. This is the return address from the perspective of the return instruction itself. So this is how we want to do, this is what we need to do first. This is our first step. After the first call to G with 4 and 5 as parameters, then we'll go back and undo this part here. Okay, this part will be gone. And then we allocate a second chunk of space. So this is step 2. This part here is already storing the result of G45. Then what we do is we will kind of do the same thing, which is, I'm running out of space here, but I'll just kind of graphically display what we need to do. We're going to do the same thing. We'll allocate another struct X over here. We'll then pass, according to the code, a 3, a 2, and then also the return value address, and then call G again. And then when G comes back, we have to undo all this part, then we'll have this part left on the stack. This return value address is from the perspective of F. And the return value of F is just going to be stored in X. So that means this return value address can just point to X, which is sitting somewhere on the stack as well. Okay, are we doing okay so far with this chunk of code? Let's see how we can do it in assembly. So I'm going to keep the picture on one side and work on the code on the other side here. Oh. It's okay. I got it. And then we want to shrink it. There we go. See? Got everything back. What I forgot to turn on or enable is a setting that I usually turn on by default, but for some reason I forgot to do this. I want my focus to follow mouse. And automatically raise no, I don't want that. Okay, that should do it. Okay, cool. Okay, this allows me to kind of interact with one window while the other one is actually on top of it. Okay, so we want to look at G this time. So we want to, nope, we want to look at main again. Okay, so we want to look at main again. We'll undo everything that is not needed anymore. So we'll go ahead and insert the code to do what we just specified that we have to do. Okay. All right. So we want to perform step 1 first, which is what this part is. Okay. So we want to subtract from the stack pointer the size of a struct X in this case, which we kind of hard code to be 8. Now remember, once again, do not use hard numbers like 8 in your code, because I am going to modify and mess around with the structure and recompile your code to make sure that your code is just using whatever the C code spews out to be the definition. Yep.
So you want us to only put numbers at the top in between global and main?
You mean here?
Yeah.
Nope, you don't want that either, because you would have the size, as a label defined in the make file. Remember last time I
And that
gave you a
defines
program?
the, program
Yeah.
that gives us, that spits off like the offsets and the
Yep.
size of it.
And that part, and that one is automatically updated whenever I update the definition of the structure. So your program should not be sensitive at all to the overall ordering and the size of the structure.
Is that make file built in?
That make file is what we talked about last time, and I did kind of go over how to make that make file. Not sure whether I upload that video.
Yeah. I
Okay.
watched it earlier today.
Okay, cool. Thank you. All right, so this is just hard coded because I don't want to go through the trouble to deal with the makefile and stuff like that. Okay, so this is just moving the stack pointer to here, but I also know that at this point, what this particular address, what is in ESP right now, is important. So I'm going to make a copy of that. I'm going to move ESP into a register. Let's make it EDX. And then I will proceed to push the parameters needed by G. This is the second call of G, by the way. So I push 5, I push 4, and then I push the return value address, which is EDX on the stack. And then at this point, I'm ready to call G. So I call G here, and since I am kind of anal about reserving space or not use extra space, I'm going to undo 8 bytes, not 12, remember? Because any subroutine that is returning a structure will automatically adjust for the 4 bytes used by the pointer to the return value area. So that's why I only have to adjust for the other 8 bytes on the stack. So this part here is taking care of step 1. I just have to do about the same thing for step 2. So step 2 is going to do the same thing, reserve another 8 bytes on the stack. In other words, at this point, I still have 8 bytes on the stack that is storing the result of G45. That is on the stack already. Now I'm dealing with the second part, which is G23. So it's going to be the same thing. Okay, so move L, ESP to EDX again, push L, $3, push L, $2, push L, %EDX, which is storing the address to the return value area. Then I call G again, and then just adjust the 8 bytes that is still on the stack that I don't need. So at this point, I have G45 on the stack, I have G23 on the stack, but now I need to supply the return value address to function function F, excuse me. I'm setting up for function F this time. So I need to specify the address of X, which is the usual stuff, okay? We push EBP on the stack. We then adjust what we just pushed on the stack by X. And then we can, that's it, okay? We have both parameters. We have the return value address pushed on the stack. Now we can just go ahead and call F. When it returns, this time, how many bytes do I have to adjust as far as the stack pointer is concerned? So in other words, I'm asking, what number should I use here? How many bytes are still on the stack that I need to deallocate just so that the stack is still balanced? Okay. 16 is correct, okay? 16 is correct because we have 2 struct X's or 2 struct X on the stack at this point. So I have to undo the space used by the 2 struct X, so that would add up to 16 bytes. And that should conclude the whole thing. Is that okay? All right. So we are thinking that this code, is doing what it is supposed to. I'm going to save this code, and I'm going to test the whole thing in C first, and then we'll test it in assembly, so that this way we know what the expected behavior is supposed to be, and then we can test the assembly code and see whether it does
what the C code is doing. Yep.
Can we see what the X is defined as again real quick?
X is a structure with I and J as members, and they're both integer types.
Well, I mean like as a label.
Oh, as labels?
Well, I mean as a label, when like for example, when you're doing the add LX like as a quantity, like how much it represents. Well, I know it represents 16, but like I just wanted to see if that's hard coded or if you're using a size up.
Okay, can you identify the number where the number is used?
27.
Line 27? You mean this X here?
Yeah, like just like
That X is defined to be ODBP minus the size of X, which is 8, but that's hard coded. So in your program, you don't want to hard code the definition of X size of, because that should come from the output of the other program that I have already kind of supplied. Is that okay? Are we ready to test the code in C, and then we'll go ahead and test it in assembly? Okay. Okay. So let's just go back and look at the C code, and this time we'll go ahead and do everything in C, so that your G and F are both written in C. What do you think is going to be in X, given the code that I have written so far? It's going to be 4-5, or 5-4, right? It's going to be 5-4 because it basically overrides X with something that's implied. Now, if I want to make this kind of less, you can just do it like this too, okay? So it will just override one of the members of X with something from Y, but the other member is going to be retained. So in this case, it's going to be a 2, because it will keep the 2 from the first parameter to F, and then the second one is going to be coming from the first member of the second call, which is going to be 4. So this time, you know, when we get back into the main subroutine, X should be 2-4. We do okay so far with this code? Okay. All right, let's check the C code first, okay? Because we need to make sure that we understand what the C code is doing before we try to implement it in assembly. So GCC-G-O main, and this time it's just the main, just the C code. GDB main, and we're going to put a breakpoint on line 29. Run the program, print X. It should be 2-4. Okay, so it is. So far so good. Okay, now this time we want to re-look at the whole thing, and this time we want to implement it in assembly, which means I am going to comment out the main subroutine, because that part is now going to be implemented in assembly, which is on this side. Are we okay so far? Okay, all right. So let's go ahead and GDB this one. GCC-G-O main.c struct.s GDB main, and we certainly want to put some breakpoints around here, particularly on line 19, which is in F. And we also want to put a breakpoint in the main subroutine itself. So I want to look at main.s, list main.s line 1. Oh, struct, forgot. And let's see, where am I going to put a breakpoint? Let's put a breakpoint on line 28 so we can examine what is on the stack. We'll put a breakpoint on line 29 after F so that we can kind of check whether things are happening the way they're supposed to. And now we can run the program. There we go, run. We're about to call F. Several things to check, okay? The first thing I want to check is what is ESP at this point, because I want to check whether it remains balanced after the call. The second thing I want to check is what is on the stack. In other words, I want to switch back to here, because at this point, other than the return address, which is the bottom part of this call frame, everything else should be on the stack. I should see the result of G45 on the stack. I should see the result of G23 on the stack. and I should also see a pointer pointing to X on the stack at this point. Okay.
So that means we have 8 plus 8 plus 4, 20 bytes to look at on the stack. So we say X, how many things? 5 things. So we have X5, WX, and that's where the stack is pointing to, which is so I can use a stack pointer to indicate where to start the dump. Okay. So does that look about right to you? So we have the lowest address has some kind of address, which is where I'm supposed to store the result. That looks like a kind of an address to me, so I'm going to assume it is correct. Then we have the result of G23, which is the structure of 2 and 3 as members, so that looks right to me too. And then we have G45 as the second parameter, so we do have 4 and 5 as the individual members on the stack. So it does look like the stack is set up correctly in order to call F. Okay? So when we single step into F, okay, this is in F, we can now examine, is X23? Yes. Is Y45? Yes. So we are basically switching between assembly and C, so that part of the code is written in assembly and part of it is written in C, but I am double checking, okay? I'm stopping in the C function just to make sure that from the C subroutine's perspective, things are passed correctly. Okay, so the C subroutine doesn't have much to do. I just need to know what is the value of X before it returns. We know that it's supposed to be 2,4. Okay, so no surprises here. Going back into the assembly code, now I want to add 16 to ESP just to undo that part of the stack. But before we do that, let's check and see what is on the stack at this point. Okay. And you can see that we got 2, 4, 4, 5. Uh-oh. No, that is correct. Okay, the 2, 4 is correct because the subroutine did change the parameter. Okay, so the 2, 4 is the parameters, is the first parameter to F, but since the subroutine did change that part is correct. And then the 4, 5 is the second parameter to F, which is still there. We didn't make it. We did not change that. We also want to check. Well, since this also displays the stack pointer, it is good. It's 700. Was it 700 to begin with? And it's 6FC. It is off by 4 bytes. It was lower before, and now it is. Now it's higher. Okay. There are some bytes that are unaccounted for. Okay, let's double check that. Pretty sure that's the case. Yeah, so the stack pointer after the call, after the add, is 700. And then before is 6FC. And this is before adding the 16 bytes. So it's not exactly balanced. But it got the work done. It's just that I lost track of 4 bytes. Okay. Let me just do this whole thing one more time. Double check it. Put a breakpoint on line 28. Run the whole program again. On line 28, check ESP. Do a next. Well, let's step into this because there's a breakpoint here. Okay, now we check ESP again. It's 700. No, that is correct because it is accounting for the 4 bytes. Okay,
Everything is good because I just forgot that those 4 bytes is already deallocated by the call lead, so it's off by 4 bytes. That's exactly what it is supposed to be. Okay, good. So everything is happening as it is supposed to be. And if you already try to do your homework assignment and you know what your homework assignment is about, I think there's a good chunk of code you can copy and paste. But figuring out which part you can copy and paste can still be a useful exercise. But if you already know which part you have to copy and paste, that means you already understand the homework assignment and what you're supposed to do well enough to actually make use of what I have presented here. So before I forget, you guys can leave if you want to because it's about time. I mean, you're not supposed to leave. You know, the dean is gonna kill me if I. Well, I guess it's being recorded, but he's gonna be displeased if I tell you guys that yeah, you can go home and have your dinner. So I will see you guys over at the lab later in 10 minutes. Okay.
I'll